we were talking about valence bond theory and looking at all of the different hybrid orbitals. And here are the instructions for how to write hybridization and bonding schemes for different molecules. So the first step is to start with the Lewis structure for the molecule. Then, using VSEPR theory, we predict the electron geometry around the interior atoms. And remember, that's looking at the number of electron groups. An electron group is a lone pair, a single bond, a double bond, or a triple bond. How many electron groups? And then you can think of your fingers, how many orbitals do I need to hybridize? So then we can select the correct hybridization. We can sketch the molecule, start with the interior atom and its orbitals, and then show overlapping with the appropriate orbitals of the terminal atoms, and then label all the bonds. So just to put your mind at ease, you will not have to draw anything for the exam, okay? For one reason, I don't want to have to look at it. My own drawings are bad, and I've been doing them a lot. So, but on the worksheet, you'll have to draw a three-dimensional representation of a molecule, but you will not even have to draw these hybrid orbitals on there, but you have to figure out the scheme and the labels, okay? And we'll have time to work on that in class, but let's do an example here. Write a hybridization and bonding scheme for xenon tetrafluoride. So the first thing we need to do is we need to start with a Lewis structure. So xenon will go in the middle, and fluorines will go around it. And then we have to think about how many electrons are we talking about. Fluorine, there's 4 fluorines. They each have 7 valence electrons. There's one xenon with 8. Remember that the group number, 8A, 7A, etc., is the number of valence electrons. So let's see, that's 28 plus 8, 36. So I already have some in the bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And I've got more electrons. Xenon is in period 3 or larger and can expand its octet. So I'm going to put those remaining 2 lone pairs on the central atom, the xenon. So now that we have the Lewis structure, I'm going to look at that central atom and ask myself, well, how many electron groups are there? There are 4 single bonds and 2 lone pairs. So 6. So there are 6 electron groups. Whoops. 6 electron groups on that central atom. So that tells me I need to hybridize 6 orbitals. So I'm going to use S, P, 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 D, and D, right? 1, 2, 3, 4, 5, 6. Still kind of on my fingers. 1, 2, 3, 4, 5, 6, right? So I get my hybridization solely from the number of electron groups on the central atom, because lone pairs will always be in a hybrid orbital. The first bond will always be a hybrid orbital. So this is why we identified electron groups the way we did, because you need a hybrid orbital for each electron group, okay? If it's a double bond or a triple bond, you'll have some unhybridized orbitals that'll take care of that. But 6 electron groups means 6 hybrid orbitals. So SPPPDD or SP3D2. So now I'm going to start with my central atom. So here's my xenon. And it's got 6, right? So this is a little hard to draw, but we've got one going up, one going down, and one kind of coming out this way, and one kind of going back that way, and one kind of coming out this way, and one kind of going out that way. So that is a very bad attempt at drawing something like this, right? It's hard to draw three-dimensional things in 2 dimensions. So let's look at this, and how many of those electron groups have lone pairs in them? 2. So here, the 6 groups, that's that octahedral shape, right? The electron geometry. And I've got 2 lone pairs. Where are the lone pairs going to go? Well, the first one, it doesn't matter. I'll make these red because for some reason electrons are red. I can make that a lone pair. And then the other lone pair wants to be where? Opposite. As far away as possible, right? So the other lone pair, that's messed up, will be over there. The single bonds are going to happen because we have a half-filled orbital from xenon overlapping with a half-filled orbital from fluorine. And so each of these has 1 electron from xenon. So if we look at xenon's, let's see, 2, 4, 6, 8, 1, 2, 3, 4, 5, 6. If we look at these hybrid orbitals, right, there's 6 of them. And how many valence electrons does xenon have? 8. 1, 2, 3, 4, 5, 6, 7, 8. So this matches up with what the Lewis diagram showed us, right? So 2 of these are lone pairs, and then what's the fluorine doing? Well, we're going to assume that fluorine is not hybridizing its orbitals. So it has just regular s and p orbitals. And how many valence electrons does fluorine have? 7. So we'd fill these 1, 2, 3, 4, 5, 6, 7. So each fluorine has 1 half-filled p orbital, and that's what it's going to overlap with these hybrid orbitals. So let's maybe make fluorine purple. So fluorine has a p orbital with 1 electron in it, and these are going to overlap. You can see why I don't want to try to grade this. Was that close enough? Oh. Doesn't look like much. So each fluorine atom has a p orbital, and the p orbital's on both sides, right? With 1 electron in it, so that half-filled orbital interacts with the half-filled hybrid orbital on xenon. We're not going to draw the rest of fluorine's orbitals, because that would really make it crazy. The rest of the orbitals have lone pairs in them. So the hybridization is this. The bonding scheme basically label the bonds, right? So all of these bonds are going to have the same label. Are these sigma bonds or pi bonds? Are they end-to-end or side-to-side? These are end-to-end. So these are sigma bonds, And they are between which two atoms? Which elements? Xenon and fluorine, right? So xenon and fluorine. And what orbital is xenon using? It's using one of these hybrid orbitals, right? So it's using sp3d2. And what orbital is fluorine using? Did fluorine hybridize its orbitals? No. So just the p. So it's just the p, a p orbital from fluorine. We're simplifying this and saying, because there's degrees of hybridization, and we definitely don't want to get into that. We just want to understand the important parts of this that are going to be helpful later on. So we don't need to think about hybridization of the terminal atoms like these fluorines. We can just look at their regular orbitals and say, well, there's that half-filled orbital. That's what's going to overlap.
So because they didn't hybridization or whatever,
Mm-hmm.
that's why we just hit P?
Mm-hmm.
Oh.
Yeah.
But if it did, then would it put S and P?
Well, if it did, then we'd have to figure out what else is going on with that fluorine and see what's going on.
Oh.
So, like, we looked at one example in lecture where we had two interior atoms, two carbons, and they had like a double bond or a triple bond or something. And then we did look at the hybridization of both of those because they were on the inside. But here, there's only the one. So all the bonds are of this type. And just for grins, what is the shape of this molecule? Well, let's look at the balloon model. So the lone pairs are the pink ones. And it's not good for pencil. What shape would the blue ones make?
Square, real square.
It's square,
Yeah.
and it's flat, right?
Yeah.
So square planar.
Oh, is that simple?
It's that simple.
Oh.
Okay, so anybody have any questions about this? I did, yes. Any questions? Yeah.
What is the first SPPD?
So this part here. So I see that there are 6 electron groups, and so I know that I'm going to take that highest floor of the hotel that has any electrons on it, the valence floor, and I'm going to need to get 6 beds into one room. I'm going to need to hybridize 6 orbitals. So I start by the elevator, and I take the S room has 1 bed, and the P room, these are 3 beds from the P room, and I'm going to need to take 2 from the D room. So I'm taking some walls out and putting in a new wall, and I'm making one big room with 6 beds in it. Hybridized orbitals. Does that help? Yeah. So I remember they tried to teach this to us in high school chemistry. It was honors chemistry, but I remember like SP3, what the heck is this man talking about? Didn't make any sense at all. Any other questions? Yeah. How did I know it's a sigma bond? That's a great question. So the first bond that forms will always be a sigma bond because that's the best kind, right? That's the end-to-end overlap. The pi bonds only happen because we can't do any more sigma bonds. So those are the leftover p orbitals, and they'll kind of bend side to side towards each other. But every bond has 1 sigma bond. A double bond has 1 sigma and 1 pi, and a triple bond has 1 sigma and 2 pi bonds. And the pi bonds are always between p orbitals, no hybrid orbitals. Just p orbitals are going to make those. Any other questions? Let's do HCN. Okay, so I'm just going to speed this up a little bit. There's the Lewis structure. Ta-da! So we have a central atom here, carbon, right? How many electron groups are on the carbon? 2. There's a single bond, one group, a triple bond, one group. Because this is a group, it's not a pair, it's a group of electrons. The triple bond has 6 electrons in it, but it still counts as one group. Because there is one sigma bond in this group, and there's one sigma bond over there. So we have 2 electron groups. And what electron geometry does that make? You've got like 2 balloons and you tie them together. What shape do they make? Linear. Makes a line. That's going to be linear. And for 2 groups, I need to hybridize 2 orbitals. So if we think about the valence shell, the valence shell for carbon. The valence shell for carbon is on the 2nd floor, right? And so we have 2s and we have 2p. And what we want to do is we have to start with the s orbital, and we're going to take one of these. So we're going to take one from the p, and then there's going to be 2 p's that are left over. And so this will be called sp. And carbon has 4 electrons, valence electrons. In the unhybridized orbitals, it's going to look like that. In the hybridized orbitals, they're going to spread out. So why doesn't this guy go over here? There's a bigger price difference, there's a bigger energy difference between an S room and a P room. When we hybridized this, when we remodeled it, this became closer in price to the P room. And now it's close enough that these guys are like, yeah, the little extra money's worth it to have my own bed, right? You know, if it was $100 a night and $200 for your own bed, like, no. But what if it was like 50 cents? Well, sure, I'll pay 50 cents to have my own bed, right? So these are going to spread out like that. And this is how carbon always makes 4 bonds. It'll never have lone pairs. So our hybridization then is sp. So when we start to draw this then, here we have carbon, and the sp hybrid orbitals, there'll be 1 on each side, and they're each going to have 1 electron in them. And then I have 2 unhybridized p orbitals left. So one will be straight up and down, and that's got 1 electron. The s orbital is where this lone pair is. So nitrogen is going to use these p orbitals to make the bonds with carbon, right? So it will take one of those, let's just put nitrogen here. One of those will make a sigma bond with with carbon. And then the other two are perpendicular. One straight up and down, one in and out of the plane. So these three half-filled orbitals, 1, 2, 3. Well, p orbitals can overlap side to side. And so these guys can overlap like that. It's a little tricky. And then the ones that are sticking out in front and behind. I know, right? They're really hard to draw. Right? In my mind, it looks a lot better. So this bond, this one up here and this one down here, that is one pi bond. And over here, this guy that's in the front and the back, one pi bond. I know it looks like two, doesn't it? But the p orbital is on both sides of the atom. It's like that standing wave, right? And even these hybrid orbitals have another little stumpy part over here. We're just choosing to ignore those to make things look better. You can see why. That'd be really bad. So then let's label these. So this one in here, is that a sigma bond or a pi bond? This one? This is sigma, it's end to end. So in there we've got a sigma bond between carbon and nitrogen, right? This is between carbon and nitrogen. What kind of an orbital is carbon using? It's using this sp, right? So carbon's using an sp orbital, and what kind of orbital is? What sort of an orbital is nitrogen using? A p. Okay with that? Now this one up here, that's the pi, right? So if you look at it from the side, it kind of looks like the symbol pi. It's got legs, right? Oops. So this one up here and this one here, those are going to be the same. Those are pi bonds, and they are also between carbon and nitrogen. What kind of an orbital is carbon using for those? It used one of these for the sigma bond with nitrogen, and it's going to use the other one for the sigma bond with hydrogen. The p orbitals are the ones that make the pi bonds. Pi bonds, p orbitals, right? P. So, p orbitals. And then this guy right here, sigma or pi? It's a sigma. I go, how do you overlap the end of an s orbital? Well, you really can't, but we're overlapping the end of that hybrid orbital. So this is between carbon using what kind of an orbital? sp. And hydrogen using what? S. When we get to this worksheet, you're going to have a lot of questions. Any questions right now?
You said the pi bond and the p orbitals, right?
The pi bonds are always just gonna be p. And the sigma will always have a hybrid orbital from the central atom.
That's a question, like, why do we write it like this? Like, CSP minus H, is there a specific reason why we write it this way, or that's just how it's?
It's just how they do it.
Oh,
I mean, if you can come up with a better way.
okay. And I was just wondering if, like, you know, if there was like a reason why they wrote it this way, or if there had a meaning besides the formula.
I don't think so. I mean, this is just, this identifies the two elements that are bonding, and this dash, it's a dash, not a minus, shows that these are connected. And then in parentheses, we've got the type of orbital that each atom is using. And up at the front, we identify what kind of a bond. So there's actually a whole bunch of information in there.